All right, a little bit about vectors today. We're going to go through a few things. If you're re-watching this video, or you're going to watch it ahead in the future, and you just want to jump to a specific section on how to do that, I'll leave time links in the description below, so you can go ahead and check those out if you want to, or just click on them and it'll jump right to the section that you want to jump to. So what we're going to go over today is vectors, right? What are vectors? And then we're going to go over how do you find magnitude, the direction, how do you find components, dot product, and how do you get the angle in between two vectors. So we're just going to be doing that a little bit today. To start out with a vector, if you didn't watch the YouTube clip, it is of Despicable Me. It's exactly correct. They go through exactly what a vector is. It is a mathematical concept used to describe the real world, and it's represented by a magnitude and direction, right? Often represented by an arrow. That's what a vector is. So some of the basics of a vector, we can draw vectors out to represent those. All we do to draw those out is we just draw like an arrow. Bam, there is a vector. That's what it is, right? It has a starting point. Usually we put a dot where it starts, and then it has the end, which is called the tail, right? The head, or the head and the tail, right? Head where it starts, tail where it ends. So that's usually what we have with a vector. Now the thing about vectors that is a little bit different than the rest of math is that it doesn't matter where we draw the vector, as long as it's pointed in the same direction and it's the same size. Vectors are equal, right? So I could take this same vector and I could move over here and draw one kind of here, and these two are essentially the same vector because I drew them at the same angle and the same size. Even though they're in different positions, they're still the exact same thing, right? If I were to draw one going, maybe a different direction, now this one here, that one is a different vector. So two of them are the same. First two I drew, the third one is not an equivalent vector. It doesn't have the same magnitude and direction. And the nice thing about that, that might seem a little complicated to start with, but the reason that works out really well is since it doesn't matter where we start drawing the vectors, for standard position, every vector starts at the origin. Just to make things a little bit easier to do the math on that, we start every vector at the origin, and then we can kind of go around. So to do the two main things with a vector, to find magnitude and direction, we're going to go over magnitude first, which is, actually not too bad. How we describe vectors, again, we can have our graph. We're just going to start at the origin and kind of put a vector in there. That's how we would draw most vectors, starting at the origin and then going out from there. How we write down vectors, if you look in your book, they will often bold out a letter when it's supposed to represent a vector. And you describe vectors much like you would describe coordinates. However, to write a vector, what you do is instead of putting round brackets around there, so if we put the point, let's say, -7, 4, right, with the round brackets around there, we know that that is a coordinate. We'd go over 7 and then up 4 in order to get to that point. But to change that to signify that, hey, I'm talking about a vector, I'm talking about an arrow connecting there, what we would do is we would not use these round brackets there. What we would do is use these kind of pointed brackets on that portion. That represents now it's a vector. But otherwise, the math is still the same. If we want to do -7, 4, again, I'm going to have to draw this on the side here. And I'm just going to draw kind of a basic idea of that. Let's go about here, -7 and 4. So there's where that point would be if we just had the round brackets. But since we've made this into a vector, we would connect from the origin and draw an arrow out to that point, right? So there is the vector -7, 4. So how do we find the magnitude of this vector, right? How do we find the magnitude of the vector -7, 4? It's quite simple. Magnitude just means size. So all we need to do is find out how large this vector is. How long is it? To do that, we use the Pythagorean theorem. So on here, we just kind of drop that down, and we have a triangle, a right triangle, and it is 7 by 4 in that case. So we do 7 squared plus 4 squared, and then take the square root. So 49 plus 16 and then take the square root of that, and that would give you the magnitude in this case. So that would be the square root of 65 in there. Yeah, so that's what we'd have there. There is the magnitude of that vector, and how we represent magnitudes is not quite with an absolute value sign, but with kind of a double absolute value sign. So if I wanted to represent the magnitude of this, so I'm going to call this V for vector, and you know, on a computer we could bold that out. Sometimes, you know, I don't have a computer, so I can't bold that. So I'm just going to put a vector arrow kind of above it, which is a line with a little extra thing above there. So this means, oh, sorry, over here, vector V, right? So to represent magnitude, right, we do that with a double absolute value of vector V. That's kind of how that would work. We put a double absolute value around it. And that means, hey, just find how far away is it from the origin. Basically, use the Pythagorean theorem. So we'd say this is equal to the square root of 65, and you could change that to a decimal if you want to. So that's how you find magnitude of vectors. How we find angles, or the direction of this, is just like finding direction around anything else, right? Just like finding angles around here. So to find the direction, we would start at our standard starting spot on the x-axis and say, how large is the angle going around here? And so you can use whatever you would want to, right? I mean, we have everything filled out here, although very simply, we know that this is 4 and 7. So if you don't want to type square roots in, I'm going to use 4 and 7. That is, you know, there's a little mini angle in here, and we have opposite and adjacent. 4 over 7, opposite adjacent, that's got to use tangent. So we could always set up and say, hey, this angle in here, which I'm going to call theta, okay, that angle has to be inverse tangent of 4 over 7 because that's opposite over adjacent. So here the angle for that vector is the inverse tangent of 4 over 7, which I know that comes off the screen there, but that's what we would do, the inverse tangent of 4 over 7. And type that in our calculator, which I've got mine fired up over here. So we would just do the inverse tangent of 4 divided by 7. And then we would hit enter on that. So we'd know that that angle in there is about 29.7 degrees on there. So when we do this inverse tangent, 29.7 degrees. Now we do have to adjust that though. Remember, just like with our solutions, we have to adjust that in here. So whenever we look for it, our angle we want from standard position. So we want to go around this way. This angle is 29.7. We want to know what's this whole angle out here. So we would subtract that from 180. We'd say 180 and 29.7 less than that. And so all we'd do is take 180 minus whatever that number was, and we could use our calculator to help double check, but that's 150.3 or 150.26 degrees on there. So that's the direction of that vector, right? So we have magnitude, which we found here. We have direction, which I guess I didn't write down, but that would be 150.26 degrees because we would move that around. That's the actual direction. Magnitude, direction, and that's the basics of finding a vector. Yeah. Now, the next thing we can talk about, the next topic, is what are called components of a vector, and those are actually quite simple to do. We actually already have the components down here. The components are -7 and 4. Those are the two components. It gets a little bit more to write them out specifically, but those are the two components. -7 is the x component, 4 is the y component. Component just means parts. Okay? Now, with vectors, we don't use x and y. We use the letters I and j. And those are the things that are meant for vectors. So the I vector just means go 1 in the x direction. That's what the I vector means. It means to go 1 in the x direction. The j vector means to go 1 in the y direction. So the I vector, if we write the letter I, okay, that would mean to go 1 in the x direction. That's what that's equal to. Very simple. It just means go 1 in the x direction. J, on the other hand, the j vector means to go 1 in the y direction. It means go up 1. So if we wanted to represent that vector -7, 4 as a set of components, right, is a little bit different. So if we wanted to represent -7, 4 as a couple of components in there, to do that here, what we would do is, since it's gone, oops, I'm going to draw that arrow out there. Since we've got -7 in the x direction, we'd say that's -7i, because that's the I vector, plus, right, -7 from this one, and we'd go 4 from the j vector of 4 in the y direction. A little bit strange, a little bit different, but it's just so that we use i's and j's to represent those vectors so we don't get that confused with coordinates, which are x's and y's. So that's the basic reason behind why those are there. It's pretty easy to do. The complicated part is just remembering, hey, they're slightly different letters than what we have. It just seems confusing right away, but really it's just x values and y values, and that's using components or the I values and j values on there. Okay? But into a little bit of new stuff. I mean, that stuff was kind of the old thing. The new stuff is how to use a dot product, okay? Or in other words, vectors you can't really multiply together so much, but we can do what's called a dot product, okay? So I'm gonna go back to this example here, how we would do the dot product. So we're gonna use our vectors. The first one that we had was -7 and 4, and we are also just gonna use another vector of, let's say, 2 and 5. Okay? So we're going to use these two vectors here. Now, if we want to do their dot product, which would just be, it's just represented very simply by a dot, right? Nothing fancy about that. But how we do the dot product, and a little bit different, what we do is we multiply the corresponding components and then add the results together. So the dot product in here would be -7 times 2 and 4 times 5, and then we would add those results together. So in here, we would take -7 times 2, and we would add in 4 times 5. That's all that there is to it. -14 plus 20. So the dot product here results in 6. And that's how we would do the dot product. You multiply their components, and then it finally becomes 6, and you add up those pieces. That's what it is. We're not going to go too much for right now into where that stuff and why that gets super, super useful. It is useful in a few different things. You know, if you go into engineering, we're just going to get the basics. That's how you use that, right? So we got that stuff down. And then to the last topic is how to find the angle in between two vectors, the angle in between two vectors. So if we had those last two where I had -7, 4, right, that would be somewhere over here, right? There's that vector, -7, 4, and then 2, 5, right? So, oops, I'm gonna draw a little more accurate here. So 2, 5, and -7, 4, right? There's where those two are. Now, a lot of times in physics, vectors are used to represent forces. So if you're pushing on something or something is pulling something else, those forces are represented by vectors. It's used a lot in engineering to build things, to make sure that buildings and bridges and things like that stand up, because you need to know what direction and how forceful everything's going on those structures. And so in here, it's very important to know what's the angle between two different forces, because depending upon how those angles are pointed, that can cause different things, and buildings can fall over, bridges can collapse. So to find the angle between two things, so for example here, if I want to know, hey, what's the angle between those two? The essential idea is that we'd be using the law of cosines. And notice we want to know what this angle is. If we really needed to, we could figure out this top side, and we have a triangle here where we have two sides, and we could figure out the third one. So we have side, side, side. So it's just using the law of cosines, but solving the law of cosines on there. Now, you guys don't have to go through the whole law of cosines. That gets really complicated. But there's a kind of formula to find the angle. And what that is, since it's based off the law of cosines, is we have the cosine of the angle between them, which I'm going to use an alpha to represent the angle right there, is equal to, okay, it's a fraction. Top stuff is the dot product of the two things. So I'm going to put V times, let's call this other one W because it kind of looks like a V, right? We're going to call these just V and W. So you do their dot product, that goes on the top. On the denominator, it looks a little bit weird, but all you do is you multiply their magnitudes together, but not their dot product. Top stuff, dot product, whoops, top stuff, dot product, bottom stuff, magnitudes. And that's how you work that out in here. So for example, how this one would go all the way through. Now we did before how we'd find their dot product in here. Okay, to get the dot product on the numerator, -7 times 2 plus 4 times 5. You need to know that. You can look that back up. And that was 6. Okay, that's how we'd find that one. Now, to find their magnitudes, again, you could look back. We did this one already. That's the square root of 65. And then we'd find this one here, which would be a 2 by 5 in there. So we could make our little right triangle if we wanted to know what the magnitude of this particular vector was. That'd be 4 plus 25. And we'd take the square root. So we get the square root of 29. Okay, so that would be the angle in between those two. Now you can go ahead and multiply that stuff out. I mean, that's not the angle itself. With the cosine of the angle is equal to this, and then we'd have to do the cosine inverse in order to find that. So if I wanted to finish going here, we could, if you want to type this in and get a number, you can. Otherwise, I'd just do the cosine inverse to find the angle in between those two. So here, that's what I'm going to put in just to show you how that would work. So here I'd have 6 over. I'd want to make sure to put my square root of 65 and the square root of 29 both on the denominator there. So there's a couple different ways to do that. I like doing that by just putting sort of a double fraction or double divide sign in there. Divide by square root of 65, divide by 29. To make sure that both of those are on the denominator. If you don't want to do that, you can put them in parentheses. You can say 6 divided by parentheses, square root of 65 times square root of 29, close the parenthesis then, so that you make sure that both of these numbers stay on the denominator. Okay, and you might want to check that out in your calculator so you make sure you understand what I'm talking about, so that you get, the angle comes out right. But what that means is the angle in between these two is the square root of 80, or sorry, not square root, is just 82.06 degrees. That's the angle in between these two vectors, and that's how you do that, or the more complicated part. And that's the main thing on those vectors, kind of the basic stuff. So again, if you need to just go back to any one of those spots, timestamps are down below there in the description. So if you need to jump back and see those examples, you certainly can.